what happens? It also becomes expensive. You're right, it becomes expensive. It's very good material, but it's expensive. Unfortunately, it's very expensive. Carbon, therefore, for civil engineering applications, we probably cannot use carbon fibers. But in aerospace industry, they always use carbon. Remember one more thing. If you cannot add carbon and steel together, okay? If you have carbon fiber and you have steel fiber, fiber or reinforcing bars, that will cause what's known as galvanic corrosion. Very big problem. So either you coat this or coat this. If not, there will be a battery effect. It's no good. So carbon fibers are very expensive, but they're also very stiff. That means the modulus of elasticity is very, very high. And then we have aramid somewhere in between. Glass fiber is not as stiff as carbon fiber. Depending on the type of fiber you use, glass fiber, S for strength, it's very high strength material, fiber. These days, the glass fiber guys, I think Corning, Owens Corning, those fiber guys, they're able to produce what's known as alkali resistant fiber, AR fiber. AR fiber is pretty good. They claim it to be stable in concrete environment. So what's common with all these fiber stress strain curves? They're all linear, and they're linear all the way up to the failure point. So everywhere here it will go linear and then fail all of a sudden. Very, very big problem. So basalt is very similar to glass. So in my work, we found that the stiffness is about, of the bars, at least with the matrix, with about 55% volume fraction, it's like 6,000 KSI. 6,000 KSI is like 6 times 7, 42. So 42,000 or 42 GPa. 42 GPa stiffness, very low. So that's the problem. If you want to develop, if any one of you want to develop a good FRP bar or FRP material, one thing you want to look at is stiffness. Strength, towards the end of this course, you'll see strength is not a problem. High strength, low strength, it doesn't matter as much as the modulus. If you have high modulus, you can utilize the strength better. That will be more obvious when we do the actual fluxural analysis. Okay, so all these, a lot of people come and talk with me regarding, and I'm sure they're talking with others also, but they come and talk with me and say, we want to test this FRP material. My question to you is, how do we improve it, make it better? I say, I need one thing from you. Give me high stiffness, and you can sell a lot of this fiber. They're not able to do that. And if you do high stiffness, it becomes very high cost material, so they cannot do it. So that's the problem with FRP material. Because of not so high modulus, with concrete, we are not able to fully utilize the strength. Even though the strength is very, very high, we will not be able to utilize all the strength. I will highlight that maybe day after tomorrow. Okay? And here we have a few numbers here. Once again, modulus is generally, you see glass modulus about 55, 69, 85, 72. Remember, these properties are for fibers, not the composite, not the composite. So they are pure fiber, just fiber. If you pick one fiber, you test it, these are the numbers you will get. So in composite, it will be far less. The strengths and the stiffnesses will be very, very small compared to this, because there the matrix will start contributing to the mechanical properties. So this will not be as strong. So carbon, generally speaking, if you want to remember something, you can remember this. Carbon has a very good stiffness, like 230, 490, even 750. It's a very, very high modulus, right? What, again, compare it with steel. Steel is 200. This carbon, you can get even 758, 441. It's stiffer than steel. So based on my statement just a couple of minutes back, these are very good candidates for structural application. Only problem is they are very, very expensive. So they cannot come to civil engineering market because of the high cost. Okay. What else? We have tensile strength. Tensile strength, these are all GPa, 3.45 GPa, which is 3,450 MPa. Very, very high strength, right? Compared to steel, almost 10 times, 8 times, 10 times. So the strength is very, very high. Tensile strength is very, very high. Okay. Elongation, again, we have about 0.5 to 4, it ranges. That's okay. Density, 2.5. Name another material that has a density of about 2.4, 2.5. Very good, thank you. So you're still awake. Good. Now it's already long day for you. We'll finish in another 2 minutes. So very good. Poisson's ratio 0.22. Again, it's similar, not similar, but slightly higher than concrete, but it's in the range. So these are some of the properties of the materials. Just the fibers. Kevlar. Yeah. Okay. Yeah, that's yeah. I'm sure I don't know the solution to that, but okay. So it's absorbing moisture. So you may have to put some coating on that, like sizing. Yeah. So yeah, I mean, you should talk with the supplier and see if they can put some coatings on your fibers. That will help. Yeah, no problem. Okay, I'll just finish up in a minute. So remember, once again, this is for the fibers, okay? These are properties for the fibers. But the composite, it depends on what epoxy you are using or what resin system you are using. So for each combination, you'll have a different property, because matrix will start contributing to the properties of the composite. Fiber is contributing to the properties of the composite. So depending on how much fiber I have, how much matrix I have, I will have a combination which is different for different volume fraction. Does it make sense? So if you use this, you have one set of properties. If you use E-glass with something else, you have another set of properties, and so on and so forth. So here we have many different properties. One is density is one thing. It's 2.07 to 1.6, so 1.6 to 1.2, something like that. Longitudinal modulus, again remember our modulus is comparison with steel, which is 200 GPa, we get about 45, 55, 37.5. So we are not there yet with normal fiber. With carbon fiber, maybe you can get slightly better properties. But we are not even touching the 200 mark here. Transverse modulus is very, very low. Very low. Normally it's very, very low. In-plane shear modulus, of course, even lower. Poisson's ratio is smaller. We will, again, theoretically, we will predict all these properties. That is what's known as micromechanics. That's what we are going to do tomorrow. Okay. So, just to get a feel for numbers, remember it's easier to remember relative numbers. So, here we have carbon AS4, carbon HMS, S-glass, all these are composites. We have aluminum, titanium, and steel. Carbon, glass, aramid, aluminum, titanium, steel. And we have the numbers here. The modulus 145, 207, and titanium is 114, so on and so forth. So aluminum is anyway 70, which is GPa. They are all less than 200, except for carbon. Okay, and the tensile strengths can be very large. That's what you see here. What's the general tensile strength of steel that we already mentioned that, or one of you or some of you mentioned that, 500, let's say. This is 3 times, almost 3 times of 500, almost. This one is about 2.5 times 500. This is 3.5 times. So strength-wise, we are way over the strength of steel. Stiffness-wise, not really. We are not there yet. So if you want to become very rich, develop a composite with very high modulus. That will sell. Okay? All right. This is a good spot to take a break. So we'll stop here. Do you have any questions? Any questions? Anything you want to talk about? I'll be around, so if you need to talk on one-on-one, I will be around.